So that clock is fast. Yeah. Okay, 45 and then which is what I thought.
Okay. So I should get it by 11:20.
Yeah, I guess so. 11:20, 11:18. Yeah. Okay, maybe. All right. So it's my pleasure to introduce David Chiang, who studies natural language processing with interest in machine translation and syntactic parsing, and he's going to tell us about transformer experience.
Thank you very much. Sorry for the kind of dull title. When I filled out the form, I didn't realize it would become the real title of the talk. So my talk is on transformer expressivity and formal logic. This is joint work with Dana Englund and my PhD student, Andy Yang. So just to kind of situate this talk is going to be about expressivity, as the title suggests. I don't really have anything to say about learning. And specifically, I'm interested in thinking about the expressivity of transformers as recognizers of formal languages. And I think in the talk so far, we've seen a lot of wide range of approaches to transformer theory. And so this talk is from a particular viewpoint of formal language theory. So let me just say a little bit about what setting we're working in. I don't need to explain to you how a transformer works, but I'm assuming throughout this talk we have a single stack of layers. We have at the last position of the last layer, we project down to a single scalar and test whether it's positive or negative, or put a sigmoid on it, test whether it's greater than half or not, and that will determine whether or not the transformer is considered to accept or reject the input stream. You could think of this as an encoder-only model, so there'd be like a BERT-style classifier where that's the binary classification, or you could think of this as a decoder-only model where this is the prompt and you have to immediately produce the next output symbol, which would be like a yes or a no. Crucially, we're not considering any intermediate steps or chain of thought here. All right, does that make sense? Okay, so if we set up a transformer like this, then you can treat it as some kind of mechanism for accepting and rejecting strings of a formal language, and we're interested in studying how powerful are transformers in this setting. So just as an example, this is a pair of problems that I really like. So if you have Boolean formulas with constants 0 and 1, no variables, we have this pair of problems that seem conceptually kind of close together, but can be separated through studying transformers in this light. So if you want to check the syntax of these formulas, the hardest part of checking the syntax of these formulas is matching the parentheses. So this is similar to a Deek language. And this is an example of a problem that a transformer can decide. So transformers are able to check the syntax of these formulas. But if you want to compute the semantics of these formulas, you want to know which ones are actually true. This is a problem that Will talked about yesterday. And this is a problem that transformers are provably not able to compute, subject to some assumptions. So polynomial number of bits of precision and the assumption that TC0 and NC1 are separated. All right, so these are the kinds of results that we'd like to be able to obtain. And this is just a shout out for an online community of people who are interested in studying neural networks and transformers in particular from the point of view of formal language theory. Daniel mentioned this already. And if you're interested, then come join us. This is organized by Lena Strobel and my student, Andy Yang. All right, so within this space of approaches, talking about transformers as recognizers of formal languages. So Bingbin talked about relating automata to transformers. Will talked about circuit complexity. Today, I'd like to talk about logic. Oh, animation, okay. So also known as finite model theory, descriptive complexity theory, we use logical formulas as ways of describing formal language. There's lots and lots of connections between this approach and circuit complexity. I just personally find logic easier to think about. In particular, we don't have to worry as much about the uniformity conditions. Oftentimes, logical formulas are more human interpretable. It could come down to a matter of taste. But one concrete way that logics have an advantage that hopefully I'll be able to show you is that logics afford a much greater degree of control over what resources you have available. And so these are some examples of things that you might be able to control. And the hope is that we'd be able to get more precise results than we would with circuits. Okay, so this is an overview of what I'd like to talk about. First, I'd like to talk about first order logic and relating them to unique hard attention transformers, which Will also mentioned briefly in his talk. And this is pretty well worked out. So there's an exact equivalence between a particular variety of transformers and first order logic. And this exact equivalence leads to many related results. So for example, you can get results saying that transformers with k+1 layers are always more expressive than transformers with k layers, things like this. And then in the second part of the talk, I would like to talk about extensions of logics that allow counting and relating these counting logics to actual transformers that use softmax attention instead of unique hard attention. All right, so that's the plan for my talk. So first order logic, this is a summary of the results of this paper by Andy and myself and Dana. And each one of the things inside the gray box is some kind of a variant of a transformer. And the paper proves all these different relationships among variants of transformers by means of this equivalence with first order logic. So the single direction arrows are strict inclusions and the double-headed arrows are equivalences. I'll come back to this later. I know it doesn't all make sense right now. All right, so what's the specific kind of transformer we're working with? This is the same picture I showed you before with a few slight changes. So we're using unique hard attention, which means that the attention is always 100% focused on a single position, one and only one position. If there's a tie, we choose the rightmost position, which is not a totally arbitrary choice. We choose the rightmost position in case of a tie. This is as opposed to average hard attention, where you would divide equally among the tied positions. So no matter what, all of the attention goes to one position. And we're using future masking, also known as causal masking. Something slightly weird is that we're using strict future masking. So each position does not attend to itself. Each position attends only to the position strictly to the left. This is not how causal masking works in practice, but this is what we need in order to get our initial results to work out. I will come back to non-strict masking later on in the talk. Okay, something a little bit weird that happens is that means the first position has nowhere to attend to. So you take the weighted average of 0 things, and we're just going to call that 0. It doesn't matter much what we choose. That seems as good a choice as any. All right, does it make sense? So we use unique hard attention, strict future masking. Okay, so how do we use logic to describe a formal language? Here's some examples. I think examples are better than going through the full definition. So first order logic, everyone's familiar with, right? The variables range over positions of the string, which we consider to be labeled numbered from 0 to n-1. And you have all the usual connectives and quantifiers, and you have these predicates Q0. So Q0 is true if and only if the symbol at position X is a 0. Here my alphabet is 0, 1. Okay, so there's also a Q1 symbol that's true if only if the symbol at that position is a 1. So this formula says for all positions, the symbol at that position is 0. So like as a regular expression, this would be 0 star. Okay, this is a language of strings that contain all zeros. So the formula would be true for this string, false for these strings. All right, slightly more complicated example. So for all positions X and for all positions Y, if X has a 0 and Y has a 1, then X must precede Y. Okay, so in English, this is every 0 comes before every 1. As a regular expression, this would be 0 star, 1 star. All right, so the formula is true here, but false here. All right, does it make sense? Okay, great. So I also want to talk about another kind of logic, which might be familiar to a lot of people, but maybe less familiar to some people, which is called linear temporal logic. And in linear temporal logic, so there's well, think of position as time. So think of the first position of the string as being the earliest in time, and the latest position of the string being the latest in time. And every single subformula of a formula of LTL, it depends implicitly on this time variable. So we used to say Q0 of X, but now we just say Q0 because implicitly it's depending on the time. So you can think of Q0 as at the current position or at the current time, the symbol is a 0. Does that make sense? Okay, and then this G inverse can be read as it has always been. So G inverse Q0 means it's always like ever from the beginning of time, which is the beginning of the string, up until now, it's been all zeros. Okay, and we evaluate the formula at the end of the string. So this is the same as before. This is 0 star. Okay, and in English you could say it's always been 0. By the time you reach to the end of the string, if it's true that it's always been 0, that's the same thing as 0 star. All the symbols are zeros. Yes. No. So we only check the truth of the formula at the last position. Yeah, I think that answers your question, right? I think it's a no. Any other questions? Okay, so if we want to do 0 star, 1 star, then we say, this is a little more complicated. So S stands for since. So that means ever since some time when it was all zeros up until then, ever since then, it's been all ones. Okay, and it's 1 right now. Okay, and if you evaluate that formula at the end of the string, that you could think of it as it was 1 since it had always been 0, and it is now 1. So there was some time when it was all zeros, and then there was some time after that when it was all ones. Is there a bug?
The first example should be false. Specifically because of the
So
and.
0 star 1 plus. Yeah,
And
you're right.
if
It's a mistake.
And Q1 wasn't there, then that would be right, right?
Yeah, I think you're right. Yeah.
Thanks.
LTL is more concise than first order logic, but it's harder to debug, I think. So as evidenced by the mistake on my slide. Yes, but it's going to turn out to be pretty convenient for a lot of these constructions. All right, any other questions? Yes.
The all zeros example would be right if it wasn't for the and Q1 at the end, right? If it was just the first part of the clause.
Yeah, that would have been a simpler formula too. But if I just erase this, there would be another bug, and that would give true to 0,0,0,1,1,0. I don't want that. So I need to go back and debug it more.
Well, why would that be?
I wanted to get 0 star 1 star.
Wait, I'm a bit confused. So why is the second one?
Why is what?
Why would the second one? If you're saying that would evaluate true, why is the second formula evaluating false? I mean, I guess I'm trying to understand the quantifier in this G minus operator. Is this a?
Yeah. So this says there's some points in the past. Yeah. There's some point in the past where it was all zeros up until that point.
Okay, and
ever since that point, it's been all ones, but not including the present time. And then this last bit is to assert that at the present time it's also 1.
oh, whoa, why not include? Oh, I see. So
That's just how S is defined.
So ever since that time, but not
But
including.
not including now.
I see.
Oh,
Yeah.
so it just is agnostic about the current time.
Right.
Okay, so I had thought that you had the and Q1 to avoid the vacuous example of it never having turned into 1, but it's really it just doesn't make any claims about right now.
Yeah. I would need to think carefully to get this formula exactly right. But yes, so and there are some variants of this logic where S does include the present time, and there's some variants where S doesn't include the present time. This is the next slide. So the questions tell me that you understand the formalism, just have a problem with my example. It's not right. Yeah.
Change it to and Q1 or G minus.
Yeah. It would be even longer.
And Q.
Okay. So yes, there's a non-strict and a strict version of the since operator. I think different conventions are more common in different application areas of LTL. We're using the strict version here. There's also an until operator that says there's some point in the future when psi is true, and then up until that point, from now until that point, that future time, phi is true. Okay, it's just the time reversed version of since. This G inverse operator can be defined in terms of S. So what we're calling LTL is the temporal logic that just has the S and U operators. Okay, so other useful things like this G inverse or just G can be defined in terms of S and U. All right, so that's LTL. And the reason LTL is useful is because you always have this implicit time variable. And that corresponds exactly to the fact that at every layer of the transformer, you've always got a sequence of vectors. And so there's always this single dimension of time. Yes? Yeah, so nonlinear temporal logic would consider branching timelines.
Okay.
Like
Okay, so
Marvel movies or things like that. What? Yeah.
Okay.
Right. Absolutely. Yeah. And I suppose if we were interested in transformers that operated on things that were not sequential, then maybe other kinds of modal logics would be interesting. Okay, so first order logic and LTL, possibly surprisingly, describe exactly the same class of languages. So this was a PhD thesis of Kemp, who is a linguist slash philosopher who was studying the phenomenon of tense. And this was his PhD thesis. The proof was like 100 pages long. There's a more modern proof that's only a few pages long, but it's not a very easy result. And this is a very well-studied class of languages. So those two are both equivalent to counter-free automata or aperiodic automata. And those are also equivalent to a restriction of regular expressions called star-free regular expressions. And so the most common, like everyday name for this class of languages is the star-free languages. And the definitions of these two things are not that important. This is just to show you that this is a well-studied, robust class of languages. So an example, kind of the minimal pair of strings that are and are not in this class. So AB star is in this class, but AA star is not in this class. And intuitively, it's because they seem so similar, but in order to verify AA, like you need to keep track of some kind of internal counter and check whether it's even in order to accept the string or not. Whereas to recognize AB, you just have to look at the bigrams. Okay, parity and majority are also examples of languages that are not in this class. Every language in this class is regular. So this is a subclass of regular, it's a subclass of AC0, and it does not include AA star. All right, any questions? So it's a pretty restricted class of languages. Yeah, so Will had mentioned AC0, this is an even more restricted class. It does include the induction heads task. So if you want to look up the previous key and then the value that was next to it, that is something that you can do within this class. Okay, so the main result of this paper is to show that masked unique hard attention transformers also recognize exactly the languages in this class. Okay, yes, so first I'll give you like a very, very brief taste of this direction. So converting from a formula from LTL into a transformer. I'm not going to show the whole proof. I'm just going to show like the basic idea. So this is kind of a cartoon version of this. So this is going to be by induction on the structure of the LTL formula. So LTL formulas have and or not, and they have since and until. So you just have to deal with these 5 cases. So if it's a not, then you just take the transformer for phi and you stick something on top. If you have an and, you take the transformers for phi and psi, paste them together in parallel, and you do something to them, and you can compute the and. And then the interesting part is if you need to translate a since or an until, and there is where you actually use the self-attention in a non-trivial way. And the since operator is similar enough to the unique hard attention that this is not too difficult of a translation. All right, does that make sense? Okay, at a very high level, of course. Okay, so to go in the other direction, our paper actually converts from a transformer back to LTL via a variation of RASP called BRASP. It's actually a little bit easier to go to first order logic. Yes?
Where do you include the fact that you're not attending to the current token?
It's related to the fact that the strict masking corresponds to the strictness of the since operator. It's strict for the same reason. Yeah. And so I'll come back to this. If you have non-strict masking, that corresponds to non-strict since. It turns out to be less powerful. Yeah. Any other questions? All right, so to go in this direction, to do this arrow that's in the paper, there's 2 tricks that are needed. To do this arrow, you just need 1 trick. So I'm going to do this, arrow that's labeled a little easier. So the 1 trick that you need is, because of the way that unique hard attention works, so this is a single self-attention layer, and here's a position that is attending to the previous layer. There's always a residual connection that just copies over the value from the same position. And then the unique hard attention always attends to exactly 1 previous position. Okay? In this case, it's attending to position 0. Okay, so that means that the value at this position always depends on exactly, sorry, at most 2 positions. Exactly 2 positions, except for the edge case of the beginning of the string. All right, so then there's an inductive proof that shows that throughout the entire computation of the transformer, there's a finite number of possible values that the transformer can ever compute. Like really, really big number of values, but it's a finite set of values. All Right? Does that make sense? And this relies crucially on the assumption of unique hard attention. Okay, if it's a finite set of possible values, then if you accept this argument, then it's not hard to imagine that you could write down some possibly very large formula of first order logic that just the formula is going to be true whether this particular bit of this particular activation is true or not. Okay, so you go by induction on the structure of the transformer and you build up this large formula. All right, so that's great. We show that LTL is equivalent. Actually, the main result in the paper shows that LTL with both since and until is equivalent to strictly masked hard attention transformers with both future and past masking. All right. So yes, so those are equivalent to the star-free languages. So now we can start leveraging results from the logic literature. So there's a paper from 1980 by Gabe et al. That says that LTL with since and until is equivalent to LTL with just since. I think there's a large blowup involved in the translation, but they have the same expressive power. So that corresponds exactly to the presence or absence of past masking. Maybe you've never heard of past masking before. Nobody ever uses it in practice. This is what people use in practice. So we have that these two transformers have the same expressive power. All right, because of something that someone proved in 1980. So in 1997, Pellet and Wilkie studied LTL with strict since as opposed to non-strict since. So if you remember, that's the difference between whether we consider the present time when we're doing the since operator. So this is something that's been studied quite some time ago. If you do non-strict since, then you get a subset of the star-free languages called the stutter invariant star-free languages. So it follows that transformers that use non-strict masking also recognize exactly the stutter invariant star-free languages. Somewhat weirdly, it means that non-strict masking is less powerful than strict masking. But non-strict masking is what we actually use in practice. Yes, question?
I'm a bit surprised.
Yeah, it's weird.
It is weird. So what is in that delta? Like, what do you need? Because it is intuitively, I guess, you can simulate, these things are mutually simulatable.
So I mentioned already that this is star-free. It is not stutter invariant star-free because this requires that there's exactly one A here and exactly one B here. But this is stutter invariant. So stutter invariant languages don't distinguish between one versus more than one occurrence of a symbol. Does that make sense? Whereas this language insists that the A's and B's alternate strictly, and like when there's an A, there's just one A, and when there's a B, there's just one B. Whereas this language says when there's an A, there can be as many A's as you want. So this is stutter invariant. This is not stutter invariant.
So you're saying you cannot recognize A, B star using a transformer?
So the strict masked transformer can do this, but the non-strict transformer cannot do this.
Wait, the bottom one it can't?
So, no, did I get it backwards? This one's easier. This one's easier.
Very easy language, right? The only thing
Because you're always going to tend to the last token, so you don't know whether it's going to be you or the previous copy of
the last language is basically anything except for something that has B's without an A, right? I guess I don't understand that language. Otherwise,
Yeah.
The only thing that is not in that language.
Yeah. This is the easier one of the two. Did I say it backwards? This is the easier one of the two.
Okay, so So the top one, as you're saying, cannot be recognized without strict
attention. Yes. Really? Yeah. This is all within the setting of unique hard attention. So I'm not necessarily claiming anything about actual transformers. Although it would be an interesting experiment to try whether real transformers behave any differently with strict attention. Strict masking. Yeah.
some assumption in the positional embedding, but it seems that you'll be able to.
This is all with no position embeddings.
No.
Yeah.
But you can create. I mean, either way, you can basically figure out where you are, right? But because you only have hard attention, so you can't figure out where you are.
Yeah.
Okay, so
Yeah.
Yes. When you only allow hard attention, you basically don't consider transformers, which is going to create like multiple hard arguments. You're not considering these transformers.
Right. Well, if there's a tie, we choose the rightmost one.
Huh?
If there's a tie in the attention score, we choose the rightmost one.
the most useful.
Okay.
No, wait, but then that language is easy. All you have to check is what was the last thing.
This one?
all I have to check is, was the last character, I just attend to like nothing, and then I get to see what the last character is, and I have to check if it's the same character as me or not.
How would you attend to the last character using all the non-strict attention?
I attend to a query of 0 and keys of 0, and a value of the current character.
That would give you the current character, not the previous character.
Ah, I see.
Yeah. With strict attention, then you can get the previous character in the way you just said. With non-strict attention, every position would just attend to itself. Okay, should I make more blue boxes? Okay, so in 2000, there was a paper on the since hierarchy. So if you consider LTL formulas and you look at the depth to which the sinces are embedded, this creates a hierarchy of languages, each one more expressive than the previous one. And that corresponds exactly. So if we do the construction that I just showed you very carefully, it preserves depth. So the depth of the transformer corresponds to the since depth of the formula. So the fact that that's a non-collapsing hierarchy in LTL means that you have a non-collapsing hierarchy on the transformer side. So this says that for unique hard attention transformers, adding more depth always increases expressive power. Two more. So now if we consider adding positional encodings, so if you add the sines and the cosines, subject to the hopefully mild assumption that the angles are all rational multiples of pi, then what you get is a logic called evomod. So this is first order logic with a modular position predicate added to it. And that's also equivalent to exactly the regular languages in AC0. So this was a logic and a class of languages that was studied in 1992. And finally, if you consider adding any position encoding, as long as the position encoding has finite image, then that corresponds to a class of languages called FOMON, which is first order logic augmented with any kind of monadic, any kind of one place predicate. All right, so this is my favorite slide of the talk because there's a lot of results that are all, 2005 was the newest one. There were a lot of previous results about this logic. Once we've proven an equivalence between transformers and this logic, then we can import a lot of existing results and draw a lot of conclusions about the relative power of all these different kinds of transformer variants. Okay, and this is what I meant before by logic allows you finer control over the resources that are available. I think it would be inconvenient to state all of these different kinds of variations in another setting. All right, any questions? Complaints? Okay, so one natural complaint would be like, this is like lamppost phenomenon, right? So yes, we found a lot of things, but the variation of transformers that we're studying is this toy variation that uses unique hard attention. So I kind of see this as, the results are interesting in themselves, but also they're like a proof of concept, I feel. So we were able to draw a lot of conclusions about unique hard attention transformers, but what we're really interested in is drawing conclusions about actual softmax attention transformers. And we're not there yet, but this picture is kind of like a aspirational goal for what we'd like to be able to show for true transformers. Okay, so that brings me to the second part of the talk. Now we're going to look at logics that are extended with a counting operator. Okay, so we were back to first order logic, and we're going to add this sharp operator that's it's like kind of like a quantifier, but it produces a number instead of a true-false value. So this is the number of positions that have a 0 in them. And this is the number of positions that have a 1 in them. Okay, and then together with these terms, we allow comparison of terms, less than, greater than, equals. We also allow plus. So this says there's more 1s than 0s. This is also known as the majority language, which Will mentioned yesterday. And we can do addition like this. So we can say the number of 0s is equal to the number of 1s plus the number of 1s. So in English, there's twice as many 0s as 1s. All right, so this allows us to describe more languages. So these are non-regular languages. Before, we were all working within regular languages. So this clearly adds some kind of power to the logic. Does this make sense? Okay, we can do a similar thing with temporal logic. This is something that was explored in a paper by Barcelo et al. So we have this Q1 operator that says the current position is a 1. So if we put a sharp in front, that counts the number of positions. That's 1. And so these two examples are the same as the ones I showed you before, but just in this more concise notation that always has this implicit time variable. Does that make sense? Okay. So here's something fun that you can do. Well, if you modify this counting operator slightly to only count positions, the current position as well as the positions to the left, that's what this arrow means, then this is the formula that describes the Deek language. So this says count the left parentheses and the right parentheses, and we always want the number of left parentheses to be at least as many as the right parentheses, right? You can never have an unmatched right parenthesis. So we assert that the number of left parens is less than the number of right parens. The number of left parens is less than the number of right parens, never. Okay, and then at the end of the string, we also assert that the number of left parens and the number of right parens is equal. All right, so this is the one-line solution to the Deek language using this temporal counting logic. And yeah, it's really important that these counting operators only count to the left. So they count on the prefix of the string. All right, does this make sense? Okay. So here's half of the results that we have so far. So let's see. So here's the first order logic with counting that I showed you before. An example language that it has is majority. So we had a paper in 2023 that showed that this first order logic can be converted to a normal form, which you could think of as the temporal logic version of this. Basically, we showed that the first order logic version of this could be converted to the temporal logic version of this, and that in turn could be converted to a softmax attention transformer. Okay, more recently, Andy has looked at the temporal logic that has this left arrow above it, and you've seen that it can do interesting things like the Deek language, and shown that also can be converted into softmax attention transformers. All right, and these conversions they're exact, so they work for any length string. So given any formula, there's a transformer, and they will do exactly the same thing for all strings without any upper bound on length. All right. Oh, yes.
What is the blowout if you want to go from K star to the transformer?
How big is the transformer?
Yeah.
That would be a question for Andy.
Okay.
I think it's not that bad.
Okay.
I think the other direction is usually the more inefficient direction. Okay, so let me talk briefly about this arrow, and then I'll briefly talk about this arrow. Okay, so if we're given a formula in this FO sharp plus, then all of the predicates in this logic are unary predicates. They're all monadic predicates. And so there's a relationship between this logic and something called monadic first order logic. Monadic first order logic has a very simple form, and there's an old result that says that you can put it into this normal form that only uses one variable. Okay, so if we do some analogous kind of transformation on this logic, which is shown here, so we started off with the formula of FO sharp plus, and then after some transformations that preserve its meaning, you end up with a formula that has just one variable. Okay, and then now that we've just got one variable, we make that into this implicit time variable. So then I guess the last step would be, well, let's just change this into sharp P and a sharp Q. All right, so there's a way of converting first order logic with counting, this like particular kind of first order logic with counting into this temporal logic with counting. And then from there, it's not too bad to convert that into a transformer. There's no special tricks involved, if I remember right. Okay, with this arrow, there is a trick involved. And so we're given a formula in this logic that has the directional counting, and we want to convert it into a transformer. And there is one tricky part, and that is dealing with counts inside a transformer. So counting is basically not a hard thing to do. If you want to count all the positions to the left that satisfy a certain property, you do uniform attention to all the positions to the left, and the values are 1 if the property is true and 0 if the property is false. Okay, that's all fine. The problem is that attention doesn't actually exactly count, it averages, right? So what we would get at each position is the number of positions that make phi true divided by 1, the number of positions that make phi true divided by 2, the number of positions that make phi true divided by 3. Okay, and then if you want to start working with these numbers, then these denominators start to get kind of pesky. This is something that happens in many papers, and there are many different solutions to this problem. We often find ourselves having to multiply by the current position or multiply by the total length of the string, and this is a recurring annoyance that many of these papers have to deal with. So one possibility is you can use some tricks with position encodings, and you can also use some tricks with layer normalization. So Andy's paper uses tricks with layer normalization in order to remove these divisions by the position. All right. Okay, so now the other side is, so that was all what kinds of logics can we simulate in transformers. Now we're interested in the other direction of what transformers under what conditions can we translate a transformer into a formula of one of these logics. Okay, I think I'm using these terms upper bounds and lower bounds in the opposite of way of what people are used to. I'd love to talk to you more about that later. Okay, so the results that we have so far, or the results that we collectively have so far. So in this ICML 2023 paper, we took fixed precision transformers. So you fix in advance a number of bits of floating point precision, and any transformer like that can be converted into this logic FO sharp plus. Okay, it's a pretty weak logic. One example of a language that it doesn't express is parity. Okay, Will talked already about his result about log precision transformers being in uniform TC0. Okay, the logical counterpoint of uniform TC0 is this logic here, this first order logic. It has a counting operator. It has plus. It also has multiplication, and it has the ability to treat positions as counts and counts as positions, which is a really, really important property. Okay, so we're calling that FO sharp plus times, and that's equivalent to uniform TC0. So Will's paper shows that log precision transformers can be converted into this. It turns out, as Will alluded to, that you can actually relax this log precision assumption. You can actually go to a polynomial number of bits and still get the translation into TC0. All right, so these are our upper bound results. And Will has argued that this is not enough precision. Like if you had a computer that could store a string of length n, then just to store the pointers into that memory, you would need log n bits in your machine words, right? And so it doesn't make sense that you would have O1 precision. Log n precision seems like the minimum that you would need. Okay. On the other hand, I feel like a polynomial number of bits seems like a lot of precision, and I just can't imagine why you would want to have that much precision. Like, why would you need 1,000,000 bits in order to process a string that has 1,000,000 symbols? It seems too much, and I agree with Will's assessment that kind of the Goldilocks level of precision is log precision. But then if you look at this picture, you say, well, the results that we have so far put both of these into the same complexity class. That suggests to me that there's probably something smaller than this that still contains log precision transformers. Okay, but I don't know what yet. So this is where we get to the open questions. Does the argument make sense? Yeah. Yes.
Do we know if there is or have a specific reason to believe that there is a separation between log precision transformers?
I don't know. Will, you mentioned something yesterday about
I don't think I have a concrete.
algorithms being, so this includes a lot of algorithms that are like worse than quadratic. What I think was the argument that you made? Okay, never mind. Sorry, I don't mean to put words in your mouth. Yeah. No, I wouldn't be able to give you specific examples. Okay, no, I have a guess. So integer multiplication is something that's definitely in this class, but in practice, people have found that is troublesome in practice. And so to me, that seems like an interesting problem that could be, I don't know about separating these two, but could be in this class, but not here, maybe. Total conjecture.
Yeah, that's equally interesting.
Yeah. Okay, so what are some possible restrictions on this logic? This logic is really expressive. It's quite surprising what it can do. Like, okay, it can't evaluate the Boolean formulas, but there are a lot of things that it can do. Most famously, this paper showed that you can divide an n-bit integer by a poly n-bit integer by another poly n-bit integer, and this lets you do things like computing truncated Taylor series and quite complicated operations that if you did them on pencil, it would take you a long time to do these calculations, but they are doable in TC0. So what are some possible restrictions that we could impose? So one very interesting one that would be a restriction to two variables. So this is something that's been studied by Krebs and other people. Not having the ability to treat counts as positions and positions as counts. So I think separating them probably could be a useful way to restrict the power of this logic. Maybe some restriction on what multiplication is able to do in this logic. But this is all still very open. My conjecture is that there is a restriction of this logic that will still be able to express transformers, but I don't know specifically what yet. Yes. Okay. Yeah, I'm about to wrap up. Yep. Okay, see, I'm about to wrap up. All right, so the take-home message that I want you to get from this talk is that logic is a useful tool for studying transformer expressivity, and I hope I've at least kind of convinced you of that. So for the case of unique hard attention transformers, we've shown that it's equivalent to first order logic and LTL, and this has given us a whole host of results internal to transformers, so results relating transformers to other kind of transformers. And these are provable guarantees about the expressivity of these different variants. And to me, that's a really great payoff of all this past work on the logic side. So we're just getting started trying to understand what kinds of logical counterparts there are to softmax attention transformers. We've got to start. We've got some lower bounds and upper bounds, or upper bounds and lower bounds. And the long-term goal is to try to get these tighter. Ultimately, if possible, finding a logic that's actually exactly equivalent to softmax attention transformers. So that's all I have for you. I'd be happy to take questions. Yeah. Oh, sorry, that means you get to choose. So like you'd have like maybe two heads are future and two heads are past. Yeah.
You said it's one or the other.
Something like that. Or maybe different layers have different masking. I don't know. Yeah, and nobody does it in practice. Yeah. Yes.
So what's exactly the difference between TC0 and like these first order logic with counting that you mentioned?
So some example languages?
Because Will mentioned that these first order logics are smaller than TC0.
Yes, like a lot. Well, so it's the first order logic is a subclass of AC0, uniform AC0. Oh, with the sharp. So what would be an example of a language that that can't be done? In the logics as I've presented them, we can't do parity.
Okay.
Parity is definitely in uniform TC0.
So transformers can't do parity if they have variables.
Transformers can't do parity if they have. Yeah, I think that's true. Yeah. There's only one way I know to do parity, and it requires computing I over n. So it requires log n precision.
Oh, I see.
Yeah. Yes.
So I'm wondering if you can, so these connections are great and very interesting. I agree that it's very useful for studying transformer expressivity. I'm wondering if you can make also connections between the complexity, the actual complexities in these different representations. So between the different logics, I mean, it's, how much does the formula get, I guess, longer when you going to transformers also, how relate the complexity of the transformer. Now the question is how do you define this complexity?
Yeah.
Because I mean that goes back to the question I also asked at the end of the round stuff. I mean, in order to understand what transformers are doing, when I'm training a transformer, if I'm kind of finding a low complexity representation in that transformer, can I think of it as finding low complexity representation?
Yeah, that's a good question. It's something that we haven't thought about too much. I mean, we've done the complexity analyses of these translations. So it's especially yes.
Yeah, curious how bad are they? Like how bad?
I'm sorry.
Like really bad? Or
Yeah,
like,
really bad. I don't remember. Like I don't remember if it's like single exponential or double exponential. It's bad. Yeah. And it's because these formulas involve enumerating all the possible numeric values that the transformer can produce. It's a really large number. Yeah, and then like multiply it over multiple layers, and you have vectors of these. Yeah, it's bad. Yeah. So that direction is really bad. But then the direction to go from the logic to the transformer, I think that tends to be fine. Although some of the logical transformations, like going from since and until to just since, those may involve an exponential blow-up also. But if you just have a formula that's already uses just since, it's already in this normal form, then it should be like linear. The transformer should be the same size.
It would be very useful to have something with bidirectional tight connection, right? If you really want to use it as a tool for understanding.
Yeah, and in this setting, we're not going to be able to do the trick of enumerating all the numeric values. So I guess I could just blue sky and say, well, hopefully the scaling will be better than up here because we don't have that trick available to us. Yes?
I think if you map transformers to TC0 circuits, the conversion from a TC0 circuit to a formula is not that bad.
Okay.
But I don't know.
Okay.
I don't remember. The
Yeah, and I think the translation from a transformer to a directly to an FO sharp formula, I think that the direct translation also should not be too bad. Yeah. Any other questions?
We can take the rest of the questions offline. So go lunch.
Thanks very much.